The fact that there are 3 abelian groups of order 8, 2 cubed, and 3 abelian groups of order 125, 5 cubed, is related to the power, and the fact that that power 3 can be written as a sum in 3 different ways, as well, a trivial sum, 3 by itself, or as 2 plus 1, which I won't think of as different than 1 plus 2, or as 1 plus 1 plus 1. And those correspond in a natural way to these different cases that we got. The summands in each case correspond to the power of the 2s over here and the 5s over there. These 3 sums, again, the first one being a trivial sum, just 3 by itself, are called partitions of the number 3 in this case. They are the ways of writing 3 as a sum of positive integers, including the trivial sum, just 3 by itself. And the number of them is 3. If I made the problem harder by saying how many finite abelian groups are there of order 10,000, 10,000 being 2 to the 4th times 5 to the 4th, the key would be to focus on the exponent of 4 and the number of partitions of 4. But there's not 4 of them, there's 5 of them. There's 4 itself, there's 3 plus 1, there's 2 plus 2, there's 2 plus 1 plus 1, and there's 1 plus 1 plus 1 plus 1. 5 partitions of 4, and therefore the number of abelian groups of order 10,000, you'd have a list of 5 possibilities of order 16, 2 to the 4th, and another list of 5 possibilities of 5 to the 4th, order 5 to the 4th, which would be 625. And combine all those, you get 5 times 5, 5 squared, or 25 abelian groups of order 10,000. We could keep going. Let's actually use Mathematica to keep going. Mathematica has a couple built-in commands related to integer partitions. One of them is the command integer partitions. For example, if I try to evaluate integer partitions of 4, it's going to give me those 4 different summands written as lists in Mathematica. 4 by itself, 3 and 1, which represents 3 plus 1, 2 and 2, 2, 1 and 1, 1, 1, 1, 1. And if I'm after the number of partitions, partitions P will do it. Partitions P of 4 should be 5, and it is. Partitions P, the number of partitions of a given positive integer, grows fairly rapidly, actually. Partitions P of 5 is up to 7. Not too rapidly so far. Partitions P of 6 jumps up to 11. Partitions P of 7 jumps up a bit further to 15. Okay, it went up by partitions P of 4, went up by 2 to partitions P of 5, and then 4 to partitions P of 6, then 4 more to partitions P of 7. Doesn't seem like it's growing that much faster, but it does grow fairly fast in the end. For example, partitions P of 100 is up to 190,569,292. This fact that Mathematica can compute these things would allow us to answer questions that would seem crazy difficult at first. For example, I might wonder, how many abelian groups are there of order, say, 2 to the 5th times 3 to the 6th times 5 to the 7th? How many abelian groups are there of order 1,822,500,000? The answer would be the product of partitions P of 5 with partitions P of 6 with partitions P of 7. 1,155 abelian groups of this order. Pretty amazing. go even crazier here. Let's make this 7 I don't know, how about a 20? How many abelian groups are there of order? That's millions, billions, trillions, quadrillions, 2 quintillion, 224 quadrillion, 731 trillion, 445 billion, 312 million, 500,000. Just change this 7 to a 20. The answer is there are 48,279 such abelian groups. Wow. The technology is there. We can do it. You can figure out how many abelian groups there are. How many non-abelian groups there are of that order, I have no clue. And maybe nobody in the world knows. Or maybe you can't even figure it out. It might be impossible to figure out. But for abelian groups, we can do it very quickly using these principles.